So is my screen visible to all of you? Am I audible? Hello? Okay, okay. So let's start the discussion. So today we will be discussing week 6. Uh, the course subject name is known as deep learning, and this course was taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering, IIT Ropar. Myself, I am Paul. I am a PMRF research scholar from IIT Kharagpur, and my responsibilities are I will be discussing some of the questions that will be very much similar to your assignment questions. So it will be easier for you when you will solve the assignment questions. Okay, so that is my duty. But before that, I always prefer to discuss some of the theories related to that week, so that it will be easier to solve the assignment. Okay, or assignment like questions. So this week we will discuss. Okay, this week we will discuss something called autoencoders. Okay, previous week what we have discussed regarding principal component analysis and the theory behind principal component analysis. That is eigenvector, eigenvalues, and linear algebra. Okay, and this week we will be focusing on this topic known as autoencoders. So, okay, yeah, this week we will be focusing on this autoencoders. Okay, so this is a structure of an autoencoder. So autoencoder has three layers. One is the input layer, second layer is the is known as the encoding layer, and third layer is known as the decoding layer. These are the three layers of an autoencoder. Okay, so autoencoder, it is a special type of a feed forward neural network. So it is nothing but a neural network only. A similar structure you must also have seen in case of neural network also, that there is an input layer, there is a hidden layer, and there is a hidden layer or more than one hidden layer, and there is an output layer. Here in this autoencoder, here in this autoencoder, we term the input layer as input layer, and then the hidden layer is known as encoding layer here, and output layer is known as decoding layer here. Okay, so these are the three layer in an autoencoder. Okay, so what is the work of this hidden layer? It encodes its input xi into a hidden representation h. Okay, so here this is an input layer, so we will be supplying our input in the form of xi in the input layer. Okay, then what is the work of this encoding layer? The encoding layer encodes your input, okay, in the form of a representation known as h. Okay, then this layer, this green layer, is known as the decoding layer. Okay, what the decoding layer does is decodes the input again from this hidden representation. So first the blue layer or the encoding layer, it encodes your input from xi to h, and what is this green layer or decoding layer does is it decodes your information from h to xi hat. Okay, so we are supplying input as xi, and we are getting xi hat as the decoded input from the decoding layer. Okay, So this is autoencoder. Okay, the model, now how the neurons in the input layer or encoding layer or decoding layer are connected with each other. The inputs are connected by weights. Similarly, we have seen in the feed forward network, same concept. The inputs are connected to the neurons of the next layer with the help of weights. Okay, these are the weights. So input of the neurons of the input layer is connected to neurons of the encoding layer by a weight W. Okay, this is the W. Now the neurons of this encoding layer is connected to neurons of the decoding layer with a weight known as W star. Okay, and then the bias we are using in this layer is known as B. The bias we are using in the decoding layer is known as C. Okay, so we have four parameters or four set of parameters, or you can say four set of parameter. One is this weight W parameter, second is this W star parameter, third is this B parameter, that is the bias of the encoding layer, and then we have a C, that is the bias of the decoding layer. Okay, now how this H is calculated? H is calculated by nothing but your weighted sum of the input neuron WXI plus the bias in a and which we pass into a function known as G. Okay, so by that we are calculating the H. Okay, someone is joining. Okay, so by that we are calculating the by that we are calculating the H. Now how we are calculating the XI hat or the decoded output? We calculate the decoded output by same thing, that is the answer that is coming in the decoding layer into our W star, that is the weights associated weight connecting the encoding layer and the decoding layer, that is W star. So W star into H plus the bias of the decoding layer, that is C, and that is passed on to a activation function called F. Okay, so again I am repeating. So here we have how many parameters? We have four set of parameter. One is W and W star, that is the weights. W is the weight connecting the input layer to the encoding layer, and W star is the weight connecting to the encoding layer to the decoding layer. And then we have bias of this encoding layer, that is B, and then we have bias of this decoding layer, that is C. And the activation function that we are using in the encoding layer is known as G. The activation function we are using in the using in the decoding layer, that is F. Okay, so these are the you can say notations or parameters. Okay, now based on this structure there can be two types of encoder. One is under complete encoder and second one is the over complete encoder. Okay, so what is an under complete encoder? So we have number of neurons in the encoding layer, number of neurons in the decoding layer. If the number of neurons in the decoding layer is less than number of neurons in the input layer, that type of encoder we call it as an under complete encoder. So again I am repeating, if number of neurons in the encoding layer is less than number of neurons in the decoding layer, that type of encoder we call it as under complete encoder. Okay, so H is a lossy function xi, it captures all the important characteristics of xi. Okay, so why we are using this under complete encoder? Because by small number of neurons we want to capture important characteristics of our input data. Okay, so for that we are using this under complete autoencoder. Now what is this over complete autoencoder? Over complete autoencoder, if number of neurons in the hidden layer is greater than number of neurons in the input layer, that type of autoencoder is known as over complete autoencoder. Okay, now what is the practical significance of this over complete autoencoder? So actually there is no practical significance of this over complete autoencoder. Why there is no practical significance? Because if we are using an over complete autoencoder, for example 1 2 3 4 5, we have 5 neurons in the input layer, and let's say we have 10 neurons in the output 10 neurons in the encoding layer. So what will happen? We will just copy the identity function, or we will copy the input of 5 neurons in this 5 in this 5 neurons of this encoding layer, and 5 will remain vacant. Okay, so there is no practical significance of this over complete autoencoder. Okay, so this is the concept. So again, what we have learned in this slide is we have discussed about autoencoder. Then we have discussed about two type of autoencoder. One is under complete autoencoder, and second is over complete autoencoder. The physical significance or the practical significance of the under complete autoencoder is we are using less number of neurons in the encoding layer, because we want to capture all the important characteristics of the input layer in a small number of neurons. So that is the practical significance of under complete autoencoder. But there is no practical significance of over complete encoder, because whenever we are using the over complete encoder, we are just copying the identity input in the hidden layer, and the other neurons remain vacant. So there is no such practical significance of a over complete autoencoder. Okay, so this is regarding autoencoder. Is this slide clear to all of you? Is it clear? Am I audible? Hello?
Yes, sir, you are audible.
Okay.
We understand.
Oh,
We understood all the slides. It's
okay.
clear.
Okay, so next move on to the next thing. What is the choice of activation function? So here you have seen there are two activation functions. One, we are using the activation function in the encoding layer, that is G, and second, we are using an activation function in the decoding layer, that is F. Okay, so we have two activation function. Now what is the choice of activation function? So there are two cases where we are why we are interested in the choice, because one case can be the input can be binary inputs. Okay, that is a number between 0 or 1. Okay, so input can be binary inputs. So for binary inputs, the type of so for binary inputs, the type of the activation function that we are using in the encoding layer, that is G, that is nothing but your logistic function. Okay, why we are using logistic function? Because our inputs are between 0 or 1, and logistic function, we know the output of a logistic function is a value between 0 to 1. Okay, 0 to 1. So that is the range of the logistic function. So that is why our encoding layer, the activation function we are using in the encoding layer is 0 to 1, is the logistic function that is range 0 to 1. Okay, now what is the activation function for the decoding layer or the output layer? So the activation function that we are using for the decoding in the decoding layer, that is again logistic function, or yeah, only logistic function. Tanh function we cannot use. Why we cannot use tanh function? Because the tanh input is from -1 to 1. Okay, but our binary input is from 0 to 1. So again we are using a logistic function in the decoding layer. Okay, so this is the choice of activation function whenever we are talking about binary input. The second case is when we are talking about real input. So whenever we are talking about real input, so in this encoding layer, generally we can use this logistic function or any sigmoid function. Why? Because we want to capture the significance of a data in a small range. So that is why we generally use this logistic function in the encoding layer. But whenever we are talking about the decoding layer, in case of this real value input, we always use a linear function. Okay, because we want the values as exact like our input. So that is why in the activation function that we are using in the decoding layer is a linear function. Okay, so that is regarding the choice of activation function. So in summary, if I tell you the summary, so there are two activation function. One is the encoding layer and second is the decoding layer. Encoding layer, we generally always use a sigmoid function, and moreover we use a logistic function more often. In the decoding layer, for the binary inputs, we are using again the logistic function. But the activation function that we are using for a real value inputs, that is linear function, because we want the correct value. Okay, so that is the choice of activation function. Now what is the choice of loss function? So whenever we are talking about this binary inputs, so binary inputs are can be treated as nothing but like probability. Okay, so probability, the range of probability is also from 0 to 1, and this binary input can be taught something sort of probability. So for that, the loss function we use for this binary inputs is binary cross entropy. Okay, and the loss function that we use for real value input, here we use the mean squared loss. Okay, so that is the thing about choice of loss function for the binary input and real value input. Okay, so is the slide clear to all of you? What is the choice of activation function, what is the choice of loss function? For two cases, one is binary input, second is real valued input. So I hope this is clear to all of you. Okay, so let's move on to the next thing, that is the link between autoencoder and PCA. So in the previous class we have discussed about this principal component analysis. Now we will see how a PCA can be compared with autoencoder. So the encoder of a linear autoencoder is equivalent to PCA if we have this four following condition. What are the condition? If we use a linear encoder, okay, that is the function that we are using in this encoding layer is the linear function. Okay, second, we use a linear decoder, that is the function we are using, or activation function we are using in the decoding layer is again a linear function. Third, the type of loss that we are using is nothing but a squared error loss, and for this, to normalize the input to this. Okay, why we are normalizing the input to this, that is a concern. Okay, so it's we are normalizing the input because in principal component analysis what we do is to find out the eigenvector and eigenvalue, what we do is x into x transpose. Okay, that is the coefficient that is the cofactor matrix. Okay, or the yeah, that is the correlation matrix. Okay, so correlation matrix is nothing but C equals to 1 by m x into x transpose. Okay, so if we want to present our this autoencoder in the form of PCA, then we have to convert our input in the form of this. Okay, how this is similar to this? See, in this bracket term, what we are doing is centering the data. Okay, this is the mean of the data 1 by m, this portion is the mean of the data. So if we subtract the mean from the data, that is known as mean centering. So we are centering the mean. The second thing is what is this 1 by root m? So see, if this is our formula, right, to find the correlation matrix, this is the formula x transpose. So if our x equals to this, okay, and xt is also xt is nothing but similar thing. So yeah, what will be our xtx? That will be 1 by m x transpose into x dash. Okay, this, if we consider this as x dash, this bracket term as x dash, so we can write this xt into x matrix for finding the eigenvector or eigenvalue. That can be written as 1 by m x transpose, x dash transpose, and x dash. Okay, so this is the covariance matrix, or whatever covariance matrix. Covariance matrix, this play an important role in PCA. That is why we convert our this input in the form of this. So again I am repeating, what is the link between autoencoder and PCA? Encoder can be seen as a PCA if we use as a linear encoder, that is the activation function we use in the encoding layer, that is a linear function. Second, the activation function that we are using in the decoding layer, that is again a linear function. Third, the loss that we are using, that is nothing but a mean squared error loss or squared error loss. And third, if we normalize the input. Okay, why we require this normalization of input? Because in PCA we calculate the covariance matrix, and this covariance matrix, and this eigenvalue and eigenvector is calculated from this covariance matrix. So if we convert our data point to this form, so this condition becomes similar, okay, because in covariance matrix also we are centering our data and then we are dividing by m. So that is nothing but this covariance matrix. That is why we have to convert all our input in this form. Then this if we convert all our input in this form, then this autoencoder can act exactly like our PCA. So this is the link between autoencoder and PCA. So four important things: one is linear encoder, second is linear decoder, third this loss function is a squared error loss, and then we need to normalize our input like this. So if we do the all the four steps, then our autoencoder will be called as PCA, or autoencoder will be equivalent to PCA. So this is the link between autoencoder and PCA. This is the theory, and proofs and all you can always refer to your lecture note. But this is the summary of this theory in short, that you, for your linear autoencoder to be equivalent of PCA, you have to follow this four conditions. Okay, so this is about this slide. So is it clear? Okay. Now we will be talking something about regularization of autoencoder. So I have told you, whenever we are using this over complete autoencoder, or take an instance of even under complete autoencoder, regularization is necessary. What is this regularization? See, in this neural network, or in this deep learning, whenever we are talking about this neural network, we have so many parameters. So what is the disadvantage of having so many parameters is, always when we are supplying our data in a neural network, we split the data in a training test, validation test, and test set. Okay, these are the three sets that we are using for splitting our data. So if our model is not regularized, or if our model is so much complex, or so many parameter, what will happen is that our model will learn our training data so well, but it will not perform well on our validation and test set data. Okay, so that is known as generalization. Okay, so our model will generalize so well on the training data, that if it will be given an unseen data like validation or test set data, it will not able to perform that good. So that is known as generalization of the model. So to avoid this generalization of the model, we use something called regularization. Okay, so regularization, how can be simplest solution is adding a term to our loss function. Okay, okay, someone is joining. Yeah, so what I was, simplest solution for doing this regularization is a L2 regularization. What is a L2 regularization? In every regularization, what we do is adding a term to our loss function. So earlier our loss function was nothing but MSE. Okay, so is our loss function. Now the L dash will be equal to L plus something called as omega. Okay, so we are adding a term to our loss function, so that loss increase. So what will happen if our loss increase? The idea is, if our loss increase, then the model will generalize less, or it will not perform so well on our training data, but whenever we'll be giving test data, it will not succumb to our training set. Okay, so our model will not generalize that well. So that is the advantage of regularization. So regularization, we do nothing but add a parameter, or add a parameter to our not parameter, add a term to our this loss function. Okay, so we just increase our loss. So that is how we do the regularization. So the simplest regularization is known as L2 regularization. So what we do in L2 regularization, that we have this theta. What is the theta combined of? Theta combined of all the parameter, that is W, W star, B and C. So we just use all the parameter, and we combine this parameter in a term called theta, and we just add lambda theta square. Okay, so we are just adding something to our loss function, that is in a term of lambda into theta square. Theta is combined of all the parameters. So that is how we do the L2 regularization. So again I am repeating, what we do in regularization is, we just increase the loss. Okay, why we increase the loss? Because we don't want to generalize our we don't want to generalize more on our training set. Okay, that is why we increase the loss of this loss of the training. Okay, how we increase the loss of the training? Just by adding a term to our loss function. So in L2 regularization, or this is the first type of regularization, what we do is we just add lambda into theta square. This theta comprises of all the parameter w, w star, b and c. So we just adding a parameter to our loss function. So that is the known as L2 regularization. Why known as L2 regularization? Because we are doing a theta square. If it is lambda into theta, that type of regularization is known as L1 regularization. But we generally use the L2 regularization, that is lambda into theta square. Okay, so that is the thing. Now if I tell you how to learn the parameters, we have done back propagation. Everyone has done back propagation. So again we have to put the formula of the back propagation, learn the w star, w, and the biases, that is b and c. Okay, so we have to learn this four set of parameters. So our model will learn by back propagation, and the neural network will learn the training data. So that is regularization. Now how we will calculate this del L theta by del W? Now when our loss was just L, that is the mean square loss, then we have calculated. Now we have now our new loss become del L theta by del W, and this is our loss. So just we have to differentiate the extra term that is added to our loss function. That is, we again have to differentiate this also. Earlier we were just focused on this. Now we have to differentiate this also to get this parameter del L theta by del W. Okay, so this is the thing. Okay, now yeah, now another trick for regularization is if we decrease the parameter. Why our model is generalizing so well? Because we have so many parameter. Because this is a neural network and we have so many parameter of weight and so many parameter of this weight in two layers. One is this weight between this input layer and the decoding layer, and second is w star, that is the weight between the decoding layer and the weight between the encoding layer and the decoding layer. Okay, so we have two sets of w, but number of w will be depending on nothing but your number of neurons in the encoding, decoding and the input layer. For example, if we have this diagram as an example, so we have 1 2 3 4 and 1 2 3 4 5 6. So we have 4 into 6 4 into 6 weight, that means we have 24 number of weight. Similarly we have this 24 number of weight for this w star also. Similarly we have 6 values for this bias value for this layer and 4 bias value for this layer. So we have so many parameters, that is 24, that is 48, then 48, 54 and 58 number of parameter that the model will learn. So that is why, as the model is learning so many parameter, it makes the model more complex, or the model will generalize to the training data so well. So our loss will be very less, but what is happening is it is generalizing the training data. Whenever we will be giving a new set of data like validation or test set, it will not able to perform well on that validation and test set. So what is the trick? Another trick can be if we decrease the number of parameter. So how we can decrease the number of parameter? If our w will be equal to w star, okay, or w star will be equal to w transpose. Okay, so in that case what we are doing is we are using the same set of weights in both this layer. So in this layer also we have 24 weights, this layer we have 24 weights, but this 24 weights are equal in both this layer. So we are actually decreasing 24 weights. So earlier it was like 58 number of parameter. Now we are doing our calculation with 34 number of parameter. So by this we can again perform a regularization, or our model will generalize less on the training data. So these are the two important trick of regularization in autoencoders. Okay, so is this clear? Up to this, is it clear to all of you? What I have told you?
Sir, I have a doubt.
Yeah, please.
Sir, I have a doubt.
Yeah, please.
Uh, how you correlate that loss function and generalization, sir? So there was you are increasing the loss function,
Yeah.
but how it results in better regularization and less generalization? Why it happens so?
Yeah, what is generalization? You have to understand what is generalization. Generalization is if our model learns so well. If our model learns so well,
Yeah.
what will happen is loss will be very close to zero. Means our training loss
Oh.
will be very close to zero. So we will
Ah.
understand that our model is learning very well, and when we will perform that thing on a test data or a validation data, our model
Fail.
will not perform better. Okay, so that is a problem. So to decrease the problem, we will increase the training loss. Okay, that is only our
Mm.
point. We will just increase our training loss whenever we
But
are
even
increase.
after the
Yeah, yeah.
even after the training will happens, but then for this also we minimize this loss means the still
For
generalization.
this also, your question must be, for this also we are using the same number of parameter, right? For this also
Yeah.
we are using the same number of parameters, but what will happen is our loss or the least loss, we are we are calculating a loss for which our or reverse, you can say, we have a loss for which we want to optimize our parameter. So now the
Mm.
loss is greater. Earlier the loss was
Mm.
less, so our parameter
Mm.
is reaching that point. If you will remember the graph, there is a graph like this. Okay, this is the loss and this is the theta. Okay, so earlier our loss was something, our least loss was something like this, and our this is the optimum theta. Okay, theta star. So that we are calculating. Now if I
Okay.
change this L to L dash, for example, now if my L dash is something, now my if my new curve is something like this. Okay, something like this. So what will happen is our loss is greater, so our parameter will not be same. Okay, so we are
Okay.
calculating parameter for more loss. So that is the
Yeah. Yeah. Yeah.
generalization. Okay, now
Okay.
this
Okay.
is,
Okay.
our theta star
New. Okay.
dash.
Okay. New
Okay,
parameters. Okay.
okay, so this is the thing. So
Yeah, understood, sir.
yeah,
Understood.
this is the thing. Or otherwise what you can do is, another simple trick is the second trick. Okay, this is the first trick, that is the L2 regularization. And the one is the simple trick, that is decreasing the number of parameter. How you can decrease the number of parameter? You cannot say that we will not supply W star. Okay, if we will not supply W star, then this layer and this layer will not be connected. But what we can do is our W star will be equal to WT. That is, we are using the same set of weights for both this layer. Okay, by this we are decreasing the number of parameter. If we are decreasing the number of parameter, then our model will give more loss. Okay,
Mm.
because we are decreasing the number of parameters. So these are the two sets for by which we are doing the regularization. There are other also that will be discussing soon. Okay, so this is
Thank
the
you.
thing.
Thank you, sir. Thank you.
Okay, this is the
Thank you.
thing. Now
Thank you.
we will be discussing about denoising autoencoder. Okay, so what is this denoising autoencoder? So our first what we have done is we have done this L square regularization, and second we have decreased the number of parameter. Now we will be saying that if our input is if our input is not if the input that we are encoding, okay, this is the encoding layer and this is the decoding layer. If the input that we are encoding is not equal to our original input, then also our loss will increase. Okay, so that is another type of encoder, or there is another type of regularization that is known as denoising autoencoder. By this denoising autoencoders also we can do the same thing, that is regularization. So again I am repeating, this is the original autoencoder. Okay, now here we have the original input that we are encoding, and that only we are decoding. Okay, now if I say we will not supply the original input to the encoding layer, but we will supply a noisy input, that is we will add some data to our input such that it becomes a noisy input, that is xi slash, or you can say xi tilt. Okay, xi tilt. If our xi, if I we change the xi to xi tilt, so this is a noisy input, this is a noisy input, this is the original input, this o input, and this is a noisy input. Okay, we will make the input as a noisy input, and this noisy input we will supply for encoding and then decoding. So again what we are doing is we are doing some kind of regularization. So this is the concept of denoising autoencoder. So denoising autoencoder, we can use different type to noise our data. One type is the simple practice, that is what we will do is we will set a value of q and we will multiply yeah like we have input in the range of 0 to 1. Now 0 to 1, like this is 0.2, this is 0, 0.5, this is 0.6, and this is 0.8. So let's me write 0.2, 0.4, let's say 0.4, 0.6, 0.8. So this is our input value. Now what I will do is just I will minus by 1, that is this will be become 0.8, this will be 0.6, this will be 0.4, and this will be 0.2. Okay, so what I am doing is I am adding noise to the input. Okay, so this is by this again what we are doing is yeah, this is 0.8, 0.6, 0.4, okay, 0.4 and 0.2. So we are adding some sort of noise. Okay, in other words, what we will do is we can say this as with probability q the input is flipped to 0, and with probability 1 minus q it is retained as it is. Okay, so that we can use for as a mode of denoising or as a mode of noising. Next thing, yeah, next thing, another thing of importance is whenever we are calculating the loss function, a loss function or loss will be calculated between this this output from the decoding layer and our original input, not from our noisy input. If we are calculating the output from loss function from the output of the decoding layer and the noisy input, what will happen is there will be no change in the loss function value, or the loss function value will be equal to our original loss. So that does not help our cause, because we want to have a regularization. Okay, so that is why what we will do is yeah, that is why what we will do is we will be calculating a loss function from this predicted output from the decoding layer and our original input, not with this noisy input. So that is the thing, that is again a thing you have to take a note of. Okay, second thing, this is a way we can do. Another way we can do is we can add a Gaussian noise. What is a Gaussian noise? Gaussian noise is what is a Gaussian graph? This is a type of Gaussian graph, or this is the bell curve. Okay, bell curve, this will have one mean, that is mu, and this will have standard deviation, that is sigma. Okay, sigma standard deviation will dictate the width of the curve, and the center of the curve will be dictated by this mean. So this is Gaussian. So Gaussian is always written by this eta 0 or 1. Okay, this is the mu, and this is the sigma square. Okay, sigma square or variance. Okay, this is how we do. So if we can add a Gaussian noise with mean 0 and standard deviation 1, then also we can convert our xi, the original input, to a xi tilt. Okay, that is a noisy input. So so any type of thing you can do. One, you can add a Gaussian noise, or you can add a probability function, or just probability function, that is you can flip the input with this q, and you can flip the input with probability q. Probability q is flipped to 0, and probability 1 minus q is flipped to 1, or it will remain as it is, or you can add a Gaussian noise. So this is the concept of denoising autoencoder. So in short, or in summary, what is a denoising autoencoder? So earlier we have only three layers: input layer, encoding layer, and decoding layer. Now after the after the input layer, we are adding a noisy layer. What the noisy layer will do is it will add some noise to the input layer. Okay, and it will make another layer known as noisy layer. So this is the only difference. Now this noise can be added in the form of Gaussian noise, or by a term called probability we can add this noise. So this is the concept of denoising autoencoders. Okay, so is it clear to all of you? Okay, so yeah, so another important thing that I should discuss, that what is the difference between this machine learning and deep learning. So the course you are studying is deep learning, and there is another thing that is very popular, that is known as machine learning. So what is the difference in this machine learning and deep learning? So AI is a big circle. So if this is a circle, this is AI. Okay, this is the AI. AI is the big circle. Now inside the AI, there is a circle known as machine learning. Okay, this is the machine learning, and inside the machine learning, there is a circle known as the deep learning. So this is the thing. So what is the definition of machine learning? It is a subset of AI that enables computer to learn patterns from data using statistical techniques. Okay, what is this deep learning? It is a subset of ML. It is not a subset of AI, but it is a subset of ML that utilizes the neural network with multiple layers to learn complex representation from data. Okay, so this is the difference. Now the key difference, if I just not focus about the definition, but what are the other key definitions? So what is regarding this architecture? Okay, so whenever we are talking about machine learning, so we use only one type of architecture, that is either decision tree or SVM or random forest, one type of algorithm. But whenever we are talking about deep learning, as we have different set of layers, right? So one, we are using the architecture known as neural network, but for each layer we can apply different type of function, that is we can use different type of activation function in different layers. So this is the major difference. Second thing is feature engineering. Okay, so machine learning requires manual feature selection and extraction. So in this machine learning, whenever you will be supplying the data, you have to make the model understand that what are the features. Okay, so if you are doing an image data, the deep learning can work because it learns the feature automatically from the raw data, but your machine learning algorithm won't work. Why it won't work is as your image is in the form of array containing pixel values from 0 to 255. So this is the feature. So that you have to make the machine learning model understand that this is the feature. So first you have to convert your image data into a new number data, then only you can apply a machine learning model. But as the deep learning model learns feature automatically, so here you need not to do the thing. So this is the most important, you can say, the difference between machine learning and deep learning. This machine learning, it requires manual feature selection extraction. In deep learning, it learns the feature automatically from the raw data. Then the data requirement from machine learning, it can work with smaller data set. And deep learning, it requires large amount of data set. Now why is this anomaly? See, machine learning, we are supplying manual we are supplying the feature, we are doing the feature selection and extraction manually. Okay, so we are giving everything to the model. But as the deep learning learns the feature automatically from raw data, so it requires more number of data to make a better supervised learning model. So this is the data requirement. Now computational power, it can run on machine learning, it can run on CPU and low power device. Again, this is again because we are doing the manual feature selection and extraction. That is why we can run this on means low memory CPU and other devices. But deep learning, as we are supplying more amount of data to have the feature extraction, to so that the model learn the feature extraction automatically from the raw data. That is why we require GPU and TPU for complex model training. Okay. Now performance in complex tasks, machine learning good for structured data or tabular data. Deep learning, it works also for unstructured data, example image, video, text, etc. This is again related to this point. So this is the main point, this is the very main point, that if we talk about machine learning and deep learning, machine learning we have to manually it requires manual feature selection and extraction, but deep learning, it learns feature automatically from the raw data. So this is the main difference between machine learning and deep learning. Okay, so is this clear to all of you? This can be asked in short question always. Okay.
Sir, for online decision making and quick responding, which one is better, machine learning or deep learning? Suppose
All.
I take an image,
Yeah.
say one car is going,
Yeah.
so in front of that camera is there.
Yeah.
So we take an image and we have to respond immediately based on the data. So what should I do? We have to
deep,
first
deep learning, always deep learning. because
But deep learning, but first
yeah,
we have to train the model, then we have to deploy it.
yeah,
So, okay. So we have to initially train on GPUs. Shall we, once the train network, can it run on CPUs?
yeah, that can run, but your fps will be lesser. fps is that frames per second.
Frames per
That is
second?
the detection
Ah,
speed. Okay, so cpu
okay,
always it will give a slow detection speed. Okay, so that is the
okay,
problem.
okay, okay. Okay, sir,
So
thank you.
do you know models do you know this neural network model for computer vision that you are asking?
Neural network model. No, no, I have not decided on that. So
Okay,
just I'm going to
there is
work
a
on that.
popular model known as YOLO. Okay, you only look once. Okay,
Uh, What's the model, sir?
YOLO, YOLO, you only look once. Okay, let me write. Yeah, YOLO,
EULO. Oh,
YOLO,
YOLO.
YOLO.
Okay,
Okay, YOLO, you
okay.
only look once. Okay, so this is a
Oh,
popular model. So there are many
okay.
version of it. The older version are like V5, V8, etc. So this code can be very much available in your any online platform. The code can be available in the form of collab notebook. Also, I will supply the code if you require. So this code, by that code, what we will you will do is, yeah, there are many steps for the processing of data, because again as you are doing the supervised learning, so you
Mhm.
cannot or you cannot supply your raw data to the model. You have to make the model understand what is the reason of interest or what is your ROI. For that you have to do a annotation process. Okay,
Mhm.
after the doing the
Mhm.
annotation process, you have to combine your annotated thing, or the annotation is nothing but giving text to your data. So you have to have the annotated data as your input data, and then you can make the model learn by many iteration. You can make the model learn, and once the model is prepared, your weight file will be generated, and that weight file you can use for deployment. Okay.
Okay, sir.
Okay.
Thank you. Now only I'm starting, so
Okay.
it will be good for me to work, see those things.
Yeah. Okay. So yeah, so next type of autoencoder are known as sparse autoencoder. Again, we are using all the autoencoders, different type of encoder for this regularization purpose only. Okay, so what is a sparse autoencoder? A hidden neuron with sigmoid activation will have value between 0 and 1, because always we have seen that in this autoencoder, in the hidden layer, what we use is this
Logistic,
yeah, logistic function or the sigmoid function. Okay,
white function.
sigmoid function. So sigmoid is all the s curves are known as sigmoid function, but logistic is 1 by 1 plus e to the power minus x. Okay, that function is known as logistic function. So we use the logistic function for the activation function for the this layer or the encoding layer. Okay, so we say that neuron is activated when its output is closer to 1, and not activated when its output is close to 0. Okay, so that we always say that a neuron is activated if its output is close to 1. Otherwise, if its output is close to 0, we say that neuron is not activated. So a sparse autoencoder tries to ensure that neuron is inactive most of the time. So we are talking about hidden neuron only, not the output neuron. We are talking about hidden neuron only. So the sparse encoder, what it tries it to ensure that the hidden neuron or this neuron of the encoding layer is inactive most of the time. Okay, so how we can do this? We can, yeah, now what can be the average value for the hidden neurons? So the average value of the hidden neurons, if we just sum of the output of all the hidden neurons and then divide it by number of neurons in the hidden layer, that is known as the average value of the activation of neuron L is given by this. Okay, so yeah, this is nothing but average value of activation for all the neurons. Okay, so this is the thing. Now what we will do is, in sparse autoencoder, what we will do is we supply a parameter called as rho hat L. Okay, and we ensured that this rho hat L will be very closer to 0. For example, say 0.005. Okay, so by supplying this, what our idea is, uh, again we are performing a type of regularization technique. Okay, so now earlier our loss was L, our loss was just L. Now our loss was L dash equals to L plus this this row this row term. Okay, This is our loss now. Okay, earlier it was just L, now our loss is L dash equals to L plus rho theta. Now this rho theta will be taking value as this. Okay, this rho theta will be equal to this. So again we are just increasing the training loss so that our model will not generalize well. Now what is this rho and rho L? Rho is nothing but rho is nothing but uh, uh, yeah, this is actually rho, this is not rho head, this is actually rho. Okay, this is not rho head, this is just rho L. So this rho L is nothing but your average of the output of the activation output of the encoding layer, average of output that is coming from the encoding layer, that is the rho L. Now this rho hat L we will is a parameter that we will set by ourselves, and that will be very much closer to this 0. Okay, so what that will ensure is our what that will ensure is this ideally most of the neuron in the hidden layer or the encoding layer will not fire. So by that what will happen is it will not able to do up the feature extraction so perfectly. Okay, so encoding layer we are doing nothing but we are just extracting the feature of the input value. So if most of the neurons in the hidden layer are sparse, or it will give a output 0. Sparse is nothing but the meaning of sparse is most of the neuron will give an output 0. So if we will ensure that most of the neuron will give an output 0, then that will ensure that our model will not learn well the features of the input layer. Okay, that is known as sparse autoencoder. And sparse autoencoder, again we are increasing the loss by this sigma theta term. Now the thing is when the sigma theta will be minimum, or when the added loss will be minimum. Our added loss will be minimum when this rho hat L that we are choosing will be equal to rho, that is the rho L or rho, that is the average value of activation of the activation of the neuron of the encoding layer. So when our rho hat L will be equal to rho L. Okay, rho L. So in that case our model will give the our model will have the low value of theta, lowest value of this sigma theta. Okay, or the added loss. So this is the concept. So again I am repeating, what is this sparse encoder? Sparse, the meaning of sparse is the output will be 0 in most cases. So what is this sparse autoencoder means is, sparse autoencoder means is we will ensure that in the encoding layer the output of most of the neuron will be 0, such that our rho L such that our average value of the activation of neuron will be very closer to 0. Okay, that is the concept of the sparse autoencoder. Okay, so we will ensure, again I am repeating, we will ensure that most of the neurons in this layer will give an output 0, so that it will not fire. If most of the neurons will not fire, what will happen is the encoding layer will not be able to do the feature extraction of the input value that will. So our model will generalize less, or we are doing, what we are doing is nothing but again regularization. So we are taking care that our model will generalize less. Okay, so this is sparse autoencoder. Now we have the last type of encoder known as contractive autoencoder. Okay, so this is an example of a contractive autoencoder. So contractive autoencoder, what we do is we use it for mostly over complete autoencoder, because over complete autoencoder will only have more chances of this regularization thing, generalization thing. So that is why we use most of this regularization thing for this over complete autoencoder only. So again we will add a loss value in the form of Jacobian matrix. Okay, so this is the added loss value. So again I am repeating, earlier our loss was L, now our loss is L dash, that will be equal to L plus another term, that is sigma. Okay, so we are adding sigma for all the regularization process. For L2 regularization, we have added this sigma in the form of something lambda into theta square. For this sparse autoencoder, we have added this regularization term, and now for this contractive autoencoder, we are adding this regularization form in the form of Jacobian matrix square. Okay, so what is this Jacobian of the encoder? Jacobian of the encoder is nothing but the change in output of the change in output of this hidden layer, or this encoding layer neuron to the rate of change of rate of change of value for the encoding layer neuron to the input neuron. Okay, so that is this. So this is the Jacobian matrix, you can say. So if I have n value, okay, if I have n inputs, so and if I have here, if I have k neurons in this layer, that is the encoding layer, if I have n neurons in the input layer, then this is a Jacobian matrix. So that is del h1 by del x1, then del h1 by del x2, del h1 by del x3, dot del h1 by del xn. Similarly, second row will consist of del h2. Okay, now first row we are consisting of this, that is h1. Second row we will be focused on this, that is h2. So del h2 by del x1, then del h2 by del x2, del h2 by del x3, del h2 by del xn. Okay, similarly for the for this kth neuron, that is del hk by del x1, dot del hk by del xn. Okay, and Jacobian matrix we have to square, so just we have to square, we have to sum, and then you have to square. So this is nothing but if you just square this matrix, so that will be sigma theta. Okay, and then as we are doing this, so we have to just calculate the determinant and then just square it, and you will be getting this sigma rho theta. Okay, this is the rho theta. And another thing about this contractive autoencoder is, okay, now the another question is how much generalization or how much regularization we want. Okay, so actually we don't want our sigma theta to be that large. Okay, we want our sigma theta to be closer to 0. That is the ideal condition, that is less that is means ideally we want our sigma theta to be close to 0. So for by that only our L dash will be equal to L. Okay, now thing is how much the sigma theta we will decrease. So we will decrease the sigma theta in such that L theta capture important variation in the data, and sigma theta do not capture variations in data. So that is the concept of regularization. So earlier we have L theta, so that capture important variation of data. So more variation it will capture, more the model will generalize. Now what our sigma theta does is it do not capture variation in data. So that is sigma theta. So we have to do a trade-off. We cannot say that sigma theta will be very large. Okay, so in that case what will happen is our model will not be able to capture important variation of data, and that will be ineffective. But we have to keep it in such a way that we only use it for regularization purpose, so that our model can also perform better on a unseen data, that is validation set or a test set. Okay, so this is the concept. So in the summary, if we say, so we have seen three type of regularization, the other type also, but mainly three type. One is this weight decaying, or this is nothing but our L2 regularization. So this term is added in L2 regularization. In sparse regularization, this term is added, and in the contractive regularization, this is the term that is added. Okay, so this is regarding the regularization of the autoencoders. So is this clear to all of you?
Yes, sir.
Okay. Okay, so so we will just see a code of a autoencoder, because that is also important. So that is why let me show you a code of autoencoder. this is a code of autoencoder I have written for difference between this under complete and over complete autoencoder. So I will not run the code, but as I have run before the class only, so output will be below the code. What if you want to try this code, you just have to open this DL code folder that I have already provided to all of you. So DL code folder, you have to open it. There is a option here written, as I am showing in my drive only, so there is no option for me, but for you there will be option here that is copy to drive. So you copy the code to your drive and you run each cell one by one and you will see the results. So in any code, what important is, first we import the necessary libraries. So here the libraries I am importing is NumPy, then TensorFlow, Matplotlib and Matplotlib. Okay, so NumPy, it is for this organizing the data. Okay, NumPy for organizing the data or forming simple calculation like this, forming any simple calculation on a vector or matrix, we use the NumPy. TensorFlow we use for this deep learning purpose, we use this TensorFlow library, and then Matplotlib we use for plotting the curves. So these are the important libraries I have imported. Now I will be performing my thing on a MNIST dataset. So MNIST, it consists of this, I think 10,000 images of the handwritten numbers. Okay, and each numbers have 28 into 28 pixel, that is 784 pixels. Okay, again I have divided the data into two set. One is the training set and the one is the test set. Okay, and then I have for doing the normalization, or I want to have the values between 0 and 1. Okay, because if my values is between 0 and 255, there will be problem for model to learn. For example, if a value is so much, a pixel has value so much and a pixel has value so less, so our model will learn the parameter better for a pixel of more value than a pixel of less value. That is why it is always better to normalize the data. So for normalization, I have divided by 255, because you know the value of pixel is between 0 to 255. Okay, so that is why I have divided by 255. And then this is the only training region. So just I have made the data like this. Okay, and then I will be using an under complete autoencoder first. Okay, so under complete autoencoder, we have just discussed what is an under complete autoencoder, and this is how you define an under complete autoencoder. So input dimension, as I have told you, each image is of 28 into 28 pixel, so that is each image is of 784 pixel. So in input layer we will have 784 neuron. Now as we are talking about an under complete autoencoder, so the number of neurons in the encoding layer will be lesser than number of neurons in the input layer. So number of neurons in the encoding layer I am using here is 32. Okay, and then this is the encoding thing, and then we will decode the output, whatever is decode the output, and number of neurons in the output layer will be equal to number of neurons in the input layer only, or number of neurons in the decoding layer will be equal to number of neurons in the input layer only. Only number of neurons in the encoding layer we have to change it for an autoencoder. Okay, if we want to have an under complete autoencoder, then number of neurons in the input layer will be less than number of inputs in the number of neurons in the input layer. Okay, so number of neurons in the encoding layer, I have used 32 neurons. Okay, then this is the model. Just to compile or just to make the model, I have used this. So we have three layer. One is the input layer, then encoding layer. Okay, so what I have done is I have coded in such a way that input layer, I have not made separate input layer. I have just told that I have not made a separate input layer, but this encoding layer only I am naming it as an input layer, and then we will do the decoding process. And then the optimizer here we are using is Adam, and the loss here we are using is mean squared error loss, because the values from 0 to 1, so we can use mean squared error loss, there is no problem. And now under complete autoencoder, this is how I have trained it. Okay, so I have trained it for 10 epochs. Okay, and then batch size I have taken at 256, because we have 10,000 data, So that is why I have taken it as a batch size of 256, higher batch size. So in normally you can take the batch size as 16, 32 or 64, anything, but as we have 10,000 data, so I have taken a large batch size, that is 256. So then we have trained the model. Now I will be defining an overcomplete autoencoder. So an overcomplete autoencoder our encoding dimension or number of neurons in the encoding layer will be greater than number of neurons in the input layer. So number of neurons in the input layer was 784, that is 28 into 28. And here, as we are using an overcomplete autoencoder, so I am using number of neurons in the encoding layer as 1024, that is greater than 784. Then again the same process, again I have just compiled the model and I have trained the model. Okay, so that is how you can train a over complete and then under complete auto encoder. Okay, and you can just visualize your data. Whenever you will visualize, you will see that under complete auto encoder your output will be a little blur, or it will have more MSE than your MSE of the the MSE of the under complete autoencoder will be greater than the over complete autoencoder. So this is the thing. But the thing is, this is the summary. Under complete autoencoder force the network to learn compress meaningful feature. As we want to learn the compress meaningful feature. So that is why under complete autoencoder help. Over complete autoencoder simply learn the identity function, that is whatever the neurons will be in the input, it will just transfer the value to the hidden neuron. Okay, so that is why it can make the identity function, making it redundant for feature extraction. So for feature extraction we don't want to use it. Visualization over complete autoencoder produces near identical image because it will have more generalization. Okay, as it will have more generalization, so it will produce near identical image. So MSE will be lower for over complete autoencoders. Why? Because it will have more number of parameter. Here for over complete autoencoder we are using 1024 parameters, but for the or 1024 neurons, but for under complete we are only using 32 neurons. Okay, so this is the summary also I have written, and you can see the result. Okay, so main thing is you need to learn how you can code the encoder. So you can code the encoder by these steps. Okay, these are the 3-4 step that is important. These are the 2-3 step that is important. One is you have to define the number of dimension, and then you have to compile the model, and then you have to train the model. So these are the 3 important steps that you should learn how to design an autoencoder. Okay, so this is the
Sir, excuse me, sir.
yeah, please.
Where to find this code? Sir, where it is shared is this one?
This you all know, in the SWAM portal below there is a problem solving session written, right?
Yeah, there's the NBS Google Drive, that one, sir. NOC25-cs21 NPTEL Google Drive shared. That one?
Yeah. Let me show you how I can show you. Yeah. So is the code clear to all of you? First, just say this.
Yes, sir.
Is the code clear to all of you? Now, can you do the coding? If I give you an different data set, can you do the encoding? Can you make an auto encoder out of it? Can you do it?
First, we have to try this one, then we have to practice, sir.
Yeah.
We need a
Means
little time.
the others also I am asking. Is it clear to all of you? Is the steps clear to all of you? Okay, I am assuming it is clear to all of you. Okay, now let me show you. This is the folder link I am giving you in the chat box. Yeah, this is the folder link. Okay, this is the folder that you can open, and all my contents will be there. Okay, this folder, either you just save this link, or you can go to the SWAM portal. Okay, below there is a thing called problem solving session. Okay, whenever you will open the
Yes.
problem solving session, a spreadsheet will open. Okay, spreadsheet will contain four names because four TAs are taking the course. So one TA is taking
Oh,
on, I think, Friday, another one is Sunday and the Monday, and I am taking class on Tuesday. Okay, so below of
okay.
the spreadsheet, okay, let me show you the spreadsheet also.
Yeah, I saw, sir.
Yeah,
I
so
saw
below
that.
of the spreadsheet my name will be there, Ayan Paul written,
Yeah,
and there will be
yeah.
a presentation folder. This is the same folder that I have given the link. Okay, whenever you will open the presentation folder, you will see all the lectures or all the presentation of the lecture that I am taking. And second thing is there will be a folder called DL codes. Whenever you will open the DL codes, all the codes will be available to you. Okay, you can just copy the one code, any code to your drive, and then run the code and see the results. Okay.
Okay, sir.
Yeah, so let's go back to our lecture. Okay, so we have discussed everything. Now we'll be moving to the question answer session. So the topics on which week 6 assignment is based on: autoencoder, under complete and over complete autoencoder, link between the autoencoder and PCA, denoising autoencoder, and sparse and contractive autoencoder. Okay, so this is the first question. You have to guess the answer first. I am giving you the question and then we will discuss the answer. Okay, so which one of the following network represents an autoencoder? Okay, so what do you think?
Sir, actually B.
B,
B,
you are,
because input layer and output layer number of is same
yeah,
and number of hidden layer is less.
yeah. Any other guesses from anyone else? Yeah. So what are the characteristics of the autoencoder? Autoencoder, we have one input layer, we have one output layer, and we have one hidden layer.
Hidden layer.
That hidden layer is known as encoding layer. The output layer is known as decoding layer. Okay. So in all this, we have one input layer, one hidden layer, and one output layer. So by that we cannot differentiate. Now, what is the second criteria? The second criteria is number of neurons in the input layer should be equal to number of neurons in the input layer should be equal to number of neurons in the decoding layer. Okay, that is the characteristics of an autoencoder. The number of neurons in the hidden layer can change, but number of neurons in the input layer should be equal to number of neurons in the decoding layer to be a autoencoder. Okay, so if I talk about the first example, so number of neurons in the input layer is not equal to number of neurons in the output layer, so this cannot be true. This second option, number of neurons in the input layer is not equal to number of neurons in the output layer. That is, number of neurons in the input layer is 3, here it is 4. So again, this is also not right. Now what about D? D is also number of neurons in the input layer is 3, number of neurons in the output layer is 2. So again, this is false. So option B is your correct answer. Okay. So this is the thing. Okay. So B, because 3 input and 3 output. So this is the option B is your right answer. So is it clear to all of you?
Yes, sir. Yes, sir.
Oh. Now question number second. Suppose we build a neural network for a 5-class classification. Okay. So number of inputs you can say are 5. Okay. Suppose for a single training example, the true level is 0, 1, 0, 0, 1. So these are nothing uh, but your value of the different neuron in the input layer. So first neuron will have value 0, second one 0, third 0, fourth 0, and fifth 1. While the prediction of the neural network are 0.25, zero point 0.3, 0.2, zero point 0.1, and zero point 0.2. What would be the value of the cross entropy loss for the example? Answer up to two decimal places. Use base 2 for log related calculations. Okay. So what is the formula of the cross entropy loss? Okay, so first of all, where we use MSE and where we use cross entropy. So we use the MSE loss when we are dealing with real value input. Okay, and we use cross entropy loss whenever we are dealing with cross entropy, whenever we are dealing with this binary value
Binary.
input. Okay, so this is the thing. So as we are dealing with this binary value input, the loss here was asked as cross entropy loss. So what is the formula of the cross entropy loss? So this is the formula of the cross entropy loss. Okay, So here we have two things, one is yi and yi hat. So whenever hat is over a over a parameter, this hat is known as prediction. Okay, so that is output, and this is the actual value. Yi is the actual value. Okay, so yi is the actual value and yi hat is the predicted value. Okay, so and this this n is nothing but number of classes or number of inputs, you can say. And second is the log base, we are taking it as base 2. So this is the formula of the cross entropy loss. Okay, so now we can calculate. How we can calculate? Just by we have the true levels, that is yi, and we have the predicted levels, that is yi hat. Now whenever our true level is 0, so whenever yi is 0, we will not take the term. Okay, that is why we have calculated only when our yi is 1. Okay, we have yi 1 for this second case and this fifth case. Okay, in this second case, when we have yi equals to 1, what is our yi predicted? Second case, our yi predicted is 0.3. So this is the thing. And when our in the fifth case, when we have the actual value as 1, what is the predicted value as 0.2. So that is this 1 into log base 2 0.2. Whenever we will be adding this, we will be getting a loss. So whenever you will be doing calculation, the first whenever you will be solving this, first it is coming around minus 1.737. Solving this, it is coming around minus 2.321. Just add this and you will be getting your loss. Okay, so your loss will be 4.06. Okay, as it is an integer type question, so this is the answer. Okay, I think it is a range type question, so your answer is between 4.0 to 4.1. Okay, so this is the thing. So main thing is just know the formula of the cross entropy loss. Okay, if you know the formula of the cross entropy loss, you can easily calculate the value, because everything is given. Your true level is also given, that is the real output, and this is the predicted level is also given, or predicted output is also given. So you have this formula where yi is the true level and yi hat is the predicted level or predicted output. So just put the value and you will get the loss. So the loss will be coming 4.06. It is in between the range 4.0 to 4.1. So is it clear to all of you?
Yes, sir.
Now let's move on to the next question. If an undercomplete autoencoder has an input layer with a dimension of 7, what could be the possible dimension of the hidden layer? Dimension is nothing but number of neurons. Okay, so what do you think? What will be the answer?
6 and 2.
6 and 2. Okay, not 0, right?
Yeah.
Yeah, not 0
Not
because 0 cannot be, because if we are not supplying any neuron to the middle
Output layer.
layer, so that is not an autoencoder. Okay, we are not doing any encoding process. So that is why your option will be between A and E. So, either A or E. Okay, so option A and E is your correct answer. Okay, others are not possible. 8, if I talk about 8, so this 8 is a
Over
over
completed.
complete autoencoder. 7
7 is
is, we cannot say it is neither under complete nor
equal.
over complete. And so your answer will be either A or
6
E.
and 2.
Okay, now I hope this is clear to all of you. Now move on to the next question. Suppose for one data point we have this feature x1, x2, x3, x4 and x5, this. Okay, these are the input values. Then which of the following functions should be used on the output layer decoder? Okay, so option A is logistic, option B linear, option C relu, and option D 10H. So any guesses for this? So any guesses for
Sir, you
this?
said sigmoid. You said sigmoid, sir, but sigmoid is not there.
We have two.
Linear.
Yeah, linear, right? Yeah, very good, linear. See, we have two activation function. One is F and the one is G, right? The
Yes,
G
sir.
activation we are using in this hidden layer or this encoding layer. This F activation we are using for this output layer or the decoding layer. So here it is asked for the output layer or the decoding layer. So regarding G is always kind of sigmoid. Okay, sigmoid. But F will be dependent on either your input or real valued input or binary valued input. When you have a binary valued input, then we can have a sigmoid function for F. Whenever we have a real value input, then we have to use the linear function or linear unit function. Okay, this relu and linear are kind of same. What is the linear function? Linear is this. Okay, that is y equals to x. What is this?
X.
Yeah, what is the y equals to x? Okay, what is this relu or rectilinear linear unit? So that is this, that is this and this. So your y equals to x provided that your x is greater than 0. But when your x is less than 0, your the y equals to 0. Okay, y equals to 0 when x is less than 0, y is equals to x when x is greater than 0. But here you can see in the inputs, here you can see we have a minus term here, and yeah, we have a minus term here. So we have to have the linear function for this set of means the input lesser than 0 also. So for this we cannot use the relu, we have to only use the linear function. Okay, logistic and tan h we cannot use, because logistic and tan h we can use for this value. Logistic we can use for value between 0 and 1.
Fine.
Tan h we can use from -1 to 1. Okay, but here our value is exceeding -1, means exceeding the range -1 to 1, and second thing we have a value -3 also. So we have to use this only this linear function. So option B is your correct answer. Okay, so this is the thing. So is it clear to all of you?
Yes, sir.
Now question number 5, what type of autoencoder is it when the hidden layer dimensionality is less than that of the input layer? This is a very straightforward question.
Under
So
complete autoencoder.
yeah, that is under complete autoencoder. Okay, because
Autoencoder.
hidden layer dimension is lesser
Yes.
than input layer. If hidden layer dimension is greater than input layer, then that type of autoencoder is known as over complete autoencoder. Okay, here it is as when the hidden layer dimensionality is less than the input layer. So here the answer is under complete autoencoder. So option A is your correct answer. Complete autoencoder, again when this number of neurons in the input layer and hidden layer are equal, that is complete autoencoder. So this is false. Over complete, this is also false. Sparse autoencoder is something else. Okay, in sparse autoencoder, the value of the average value of h the average value of h, if there are m neurons, the average value of h will be equal to 0. Okay, that is the average value of the neurons in the hidden layer will be close to 0. So that is sparse autoencoder. So option A is the correct answer. Okay, yeah, option A is the correct answer. Okay, so is it clear to all of you? Very straightforward
Yeah.
question. Yeah,
Yes, sir. Yes, sir.
yeah. So we are question number 6. We are given an autoencoder A. Okay, the average activation value of the neuron is in this red network is 0.06. Okay, the given autoencoder is contractive autoencoder, over complete autoencoder, sparse autoencoder, and denoising autoencoder. Any guesses for
Sparse
this?
autoencoder. Sparse
Sparse,
autoencoder.
yeah, sparse autoencoder, right? Whenever we are talking about average activation value of the neurons
There
in
is
the encoding layer, so that type of autoencoder is known as sparse autoencoder, such
sparse
that
autoencoder.
the average value is very closer to 0. As this value 0.06 is very closer to 0, then we can confidently say that it is an example of sparse autoencoder. Okay, so this is the thing. Yeah, so that is the thing, because most neurons are inactive in that layer, so
Inactive
it will,
doing.
yeah, it will do the generalization process, it will do the regularization process. Okay,
This is
so
process.
option C is the correct answer. Okay, this is the thing.
So can I leave, sir?
Yeah, yeah, please, if you don't feel okay, you can leave, no problem. This session will be available in the YouTube channel. Okay.
Okay, sir. Thank you.
Which of the following problem prevents us from using autoencoder for the task of image compression? Option A, images are not allowed as input to autoencoder. Option B, difficulty in training deep neural network. Option C, loss of image quality due to compression. Option D, autoencoders are not capable of producing image output. So what do you think? Okay, so let's discuss the example one by one. So images are not allowed as an input to autoencoder. Autoencoder are what? Deep learning
Yeah.
framework or the feed forward network only. Okay, so in deep learning framework you can supply image, because deep learning framework learns the feature itself from the raw data, so we can supply image to a deep learning framework or any this feed forward neural network. So autoencoder are nothing but feed forward neural network. So this is the first statement. Okay, second, difficulty in training deep neural network. Okay, so which of the following problem prevents us from using autoencoder for task of image compression? So no, is no difficulty in training deep neural network, because we are applying some great optimizers like Adam, and also we are doing back propagation, so we have no difficulty in training the deep learning network. So this is also correct. Loss of image quality due to compression, as whenever we are talking about this under complete autoencoder, like this is four data, and this is also 4 1 2 3 4. So whenever we are talking about this under complete autoencoder, what it does is it does the image compression. Okay, because here we are using less number of neurons in the hidden layer, or this encoding layer, so there will be loss of image quality due to compression, as we have seen in the code also. We have under complete and over complete autoencoder. In under complete autoencoder, there is a the output that we are whenever we are reconstructing the image, the output is slightly blur. Okay, so the image is going undergoing compression. So option C is correct. Option D, autoencoder are not capable of producing image output. Again, this is a false statement,
Oh,
because whenever we are this reconstructing by the decoding layer, we can produce image output only. But only cases if we are using this under complete autoencoder, the output image produced will be of lower quality, because compression is going on. So option C is your correct answer. Okay, so this is the thing. Yeah, yeah, this is the thing. Okay, option C. What's the question? Yeah, option C is your correct answer. Okay, so this is regarding question number 7. So is it clear to all of you? Yeah. Now question number 8. Earlier was question number 7. Yeah. Now question number 8. Which of the following is a potential disadvantage of using autoencoder for dimensionality reduction over PCA? So in compared to PCA, what is the potential disadvantage of using autoencoder? First, autoencoder computationally expensive, may require more training data. Okay. Autoencoder are bad at capturing complex relationship in data. Okay. Autoencoder may overfit the training data and generalize poorly to a new data. Okay. Autoencoders are unable to handle linear relationship between data. So any guesses for this? No guesses. Okay. So option A as well as option C is your correct answer. Why? Because autoencoders are computationally expensive and they require more training data than PCA. Whenever we are doing PCA, we are just converting to a covariance matrix, and we are calculating the eigenvector values, and then we are projecting our data onto that basis consist of our eigenvector, and then we are doing nothing but we are doing a dimensionality reduction in case of PCA. But whenever we are talking about autoencoders, we are not doing any dimensionality reduction, that sort. Okay, so that is why it is computationally expensive and require more training data than PCA. Another thing is autoencoder, it is totally a feed forward neural network, so it is learning the data, learning feature from the raw images only. So we have to supply more amount of training data. So option A is correct. Option B, autoencoder are bad at capturing complex relationship. This is not correct. It is a feed forward neural network, so there is no such thing that it is bad at capturing complex relationship of data. Option C, autoencoder may overfit the training data and generalize poorly to a new data. Yeah, very right. As whenever we are using over complete autoencoder or under complete autoencoder with so many parameter, what it will do, it will overfit the training data and generalize poorly to a new data. Okay, option D, autoencoders are unable to fit linear relationship between data. This is again wrong. The relationship will be dependent on the activation function. So whatever the activation function you will be using, the relationship will be based on that. So again, this is a false statement. Okay, so this is false, and we are only left with A and C is your correct answer. Okay, so option A and C, the technically it is written over here, you can read it. Okay, so option A as well as option C is your correct answer. So is it clear to all of you?
Yes, sir.
Now question number 9, which of the following is a potential advantage, not a disadvantage, potential advantage of using an overcomplete autoencoder? Reduction of risk of overfitting, ability to learn more complex and non-linear relationship, faster training time to compress the input data. So what do you think?
Ability,
Yeah.
ability to learn more complex and nonlinear representations.
Yeah, because as we are using more number of neurons in our this encoding layer, so the model will have more ability to learn complex and non-linear representation. Reduction of risk of overfitting, no, it has more risk of overfitting because we are using more number of neurons in the hidden layer, as well as we are increasing the number of parameters also. So that is why there is always a risk of overfitting. This is false. Faster training time, as we are doing with with more number of neurons as well as more number of parameter, that is W star parameters. So that is why it will have more training time. So this is
Training
also
time.
false. To compress the input data, no. This is a characteristics of under complete autoencoder, not a over complete autoencoder. So this is also false. So option B is the correct answer. Okay. Yeah, option B is the right answer. So is this clear to all of you?
Yes, sir.
Now we are left with the last question, which of the following is a key difference between a sparse and a contractive autoencoder? Option is sparse autoencoder aims to reduce the number of non-zero zero activation in the hidden layer, while contractive autoencoder aim to make the encoder's output less sensitive to small change in input data. Okay. So sparse autoencoder penalizes large weight in the network, while the contractive autoencoder focus on reconstructing the data with less distortion. Okay, sparse autoencoder use a linear activation function in the hidden layer, while contractive autoencoder use a non-linear function in the hidden layer. So option C cannot be true. There is no autoencoder which tells that what type of function you have to use in the input and the hidden layer in the this yeah in the hidden layer or the output layer. There is no autoencoder, so option C should be false. Option D, sparse autoencoder require a large amount of labeled data, whereas contractive autoencoder can operate effectively with smaller labeled data set. So again, this does not make sense. No autoencoder does that more data. Whenever we are doing the regularization process, so we want a smaller data set only. So that is why this is also false. Now what about B? Sparse autoencoder penalizes large weight in the network. So this is the characteristics of L2 regularization. Okay, L2 regularization. Not the sparse encoder. It penalizes large weight in the network. So that is the characteristics of L2 regularization, not your sparse autoencoder. While contractive autoencoder focus on reconstructing the data with less distortion. Again, no sense. So option B is also correct. So option A is the correct answer. Sparse encoder aim to reduce the number of non-zero activation in the hidden layer, because again we are setting the value of rho L such that its value is very closer
Why
to
not
0.
5?
Yeah, very closer to 0. So while
0.
contractive autoencoder aim to make the encoder output less sensitive to the small change in input data. That is, we are doing the Jacobian matrix. What is the Jacobian matrix? Jacobian matrix consists of element dh by dx. Okay, h is the output of the output of the
Uh,
encoding layer, and x is the input value. Okay,
Input.
so
Okay.
our contractive
That is
autoencoder
minimized.
aim to make the encoder's output less sensitive to small change in input data. So option A is also only correct. Option B, C and D are wrong. So option A is the correct answer. Okay. So this is the thing. Okay. So by this, our questions are over. So any doubt in today's lecture?
No doubt, sir. Clear.
Okay. Okay. So So no doubt, right? So summary, what we have discussed, something known as autoencoder. Okay, autoencoder is nothing but it is a feed-forward neural network only. It has three layers: input layer, hidden layer, and output layer. Input layer is called as input layer, hidden layer is called as encoding layer, output layer is called as decoding layer. Okay, then what we have learned is two type of autoencoder: under complete and over complete autoencoder. Okay, under complete autoencoder, when we want to compress or when we want to learn important features of the input layer, we use the under complete autoencoder. Otherwise, we use the over complete autoencoder. The problem with over complete autoencoder most of the time is it generalizes the training data and it does not perform well on the test data or validation data, whatever. Okay, it does not perform well on the other kind of data, than the training data. So that is a problem of the generalization problem. So for that we use regularization. We have used different kind of regularization. One kind of regularization is known as L2 regularization. Second kind of regularization we have used is something called denoising autoencoder. That is, we have changed the input to a noisy input. Third is we have used this
Sparse.
sparse
Sparse.
autoencoder, in which the hidden neurons are we have set a parameter such that output of the hidden neurons or the encoding
Mostly inactive.
that will be average value of the neurons in the encoding. Output of the encoding layer is close to zero, and then there is this contractive
Contractive.
autoencoder. So that is the whole thing that we have learned in today's class. Okay. Okay, so by this I am ending the session for today. Everyone know where is the content available, I hope. So by this,
Sir, YOLO, you said sir, excuse me.
yeah, yeah.
You said YOLO that network now, sir. Which one is best, sir, in web page to search for about to study that one?
Which one is best means which version is
Uh,
best?
No, no, which version? I have no idea about it. I am saying which website I can go for learning those things and downloading it.
Website, you can just see the YouTube. You will get videos of it. There is no
Ah,
particular website, but there is a website called RoboFlow. Okay, RoboFlow.
Ro-
Let me write it.
RoboFlow. Okay,
Yeah,
okay, okay.
RoboFlow. RoboFlow. So you can see this website. This is a website, but you can search like RoboFlow notebooks. Okay, so RoboFlow notebook will have many Google Colab notebooks. So you can use a notebook related to YOLO, and then fit your training data. You have to fit your training data, and then you can
Uh,
run the
See how
Colab
it
notebook
works.
to have your own custom weight, and then you can use that custom weight to deploy in a real-time scenario. Okay.
Okay, sir. Thank you.
Okay, so by this I am ending the session for today.
Thank you, sir. Thank you.